For over a century, scientists have tried to explain a universe that behaves like nothing we were ever taught to expect. A reality where particles can be in two places at once, where observation itself changes what is real, and where empty space hums with invisible energy. This is the world of quantum physics, the strange, beautiful, unsettling set of rules that underlie everything from starlight and bird navigation to the devices in your pocket. In this journey, we'll trace its story from candlelit experiments and whispered debates to teleportation, entanglement, and the hidden order beneath reality itself. A realm so bizarre it makes science fiction look ordinary. In the final years of the 17th century, when the streets of Cambridge were still lit by lanterns and the night was something one walked carefully through, there were rooms where the glow of a single candle was not meant to keep darkness at bay but to invite it closer. It was in such a room, lined with the tools of a patient mind, polished glass prisms, small mirrors, sheets of parchment scribbled with figures, that a young Englishman named Isaac Newton, born in 1643, and by then already known for his restless curiosity, began to ask questions that seemed, at first, almost childish in their simplicity. What was light, and why did it behave the way it did? Why did it scatter through windows and throw colors across rain-soaked cobblestones after a storm? Why did shadows fall sharp in one moment and soften into nothingness the next? The answers were not written anywhere, so Newton decided to make the light speak for itself. He would sit alone for hours in his chambers at Trinity College. His only company, the steady flame of a tallow candle and the cold gleam of glass ground by his own hand. When the light passed through a small hole he had bored into the shutters, he guided it through a prism, a simple wedge of transparent crystal no larger than the palm of his hand. What happened next was something he must have known was possible. Sailors and scholars alike had seen rainbows for as long as people had looked up after storms. Yet to witness it in that quiet room was to feel the world become less certain and more wondrous at once. The narrow beam did not remain white. It blossomed into a band of colors, each shade stretching gently into the next. A spectrum of crimson, orange, yellow, green, blue, and violet cast faintly against the far wall. This was no trick of glass or candle. It was, Newton realized, a property of light itself, a clue that what people called white was not pure, but composed of many different forms combined. In 1666, he recorded his observations and repeated the experiments again and again, using different angles, different materials, even splitting and recombining the colors to show that they were part of a single whole. By the time he published his work decades later in optics in 1704, the simple scene of candlelight through a prism had become a quiet revolution. It suggested that nature's appearances were layered, that beneath what the eye believed it saw was a deeper order, precise and structured, waiting to be revealed by those willing to look closely enough. Yet, Newton's experiments were more than just clever demonstrations. They were small acts of rebellion against the accepted view of the world, which still held to the idea going back to Aristotle and beyond, that light was a simple emanation from objects, or a wave moving through an invisible medium called the ether. To split light into its hidden colors was to show that nature was not simple, that even something as ordinary as sunlight slipping through a window carried secrets beyond the reach of ordinary senses. And in this realization lay the seed of something even greater. The notion that the universe might be governed by laws that were invisible yet universal, that the same patterns shaping a beam of light might shape the stars above or the fall of an apple from a tree, the world beyond. Newton's room continued on unaware, merchants haggling over spices at the market, farmers marking the seasons by the tilt of the sun. But the small discoveries of candlelit nights like his were already setting humanity on a new path. The prism, a simple piece of glass, had become a window into a hidden structure of reality. It would not be the last time such a window was opened. In the centuries that followed, scientists from Thomas Young to James Clerk Maxwell would build upon what Newton had uncovered, exploring how light could behave like waves and particles, how it could bend around objects and carry messages across oceans. The flicker of curiosity he had kindled would grow into a blaze of understanding, guiding explorers not only of light, but of matter itself, it is easy, centuries later, to forget the simplicity of those first steps. We speak now of photons and electromagnetic spectra with the confidence of familiarity. But the beginning was far humbler. A man alone with a candle, asking questions that seemed too simple to matter. And yet, in the long glow of that single flame, the outlines of a much stranger world were already forming. One where the visible was only the surface of the invisible, and where every beam of light was a messenger carrying secrets from the heart of the universe. It was here, in the soft light and deep shadows of those early experiments, that the story of quantum physics began, not with equations or accelerators, but with curiosity, patience, and a willingness to listen to what the world had been whispering all along. In the spring of 1801, inside a modest London townhouse far removed from the grand halls of the Royal Society, a quiet experiment unfolded that would unsettle centuries of certainty and open a doorway into one of nature's most elusive secrets. The man at the center of it was Thomas Young, a physician by training and a restless thinker by nature who believed that light, that ordinary suspant, familiar companion of daily life, might not behave in the way everyone had been taught. Since the days of Isaac Newton, whose experiments with prisms and reflections had so profoundly shaped scientific thought in the late 1600s, the prevailing belief had been that light was composed of tiny particles streaming outward from their sources. This particle theory had an elegance and simplicity that few dared question, and for more than a century it stood as accepted truth. But Young, born in 1773 and trained in both medicine and physics, was not content with elegant explanations. He wanted to see for himself what light would do when asked the right question. His laboratory was not the polished, bustling facility one might imagine today, but a small, darkened room whose windows were covered with heavy curtains to keep out the unwanted glare of the London sun. On a wooden table, carefully cleared of distractions, he placed a screen, a narrow barrier, and a candle, simple tools that, in their simplicity, could reveal something profound. The heart of the experiment was a thin card into which Young had cut to slender parallel slits, barely a hair's breadth apart. He positioned it so that light from the candle would pass through these openings and fall upon the screen beyond. The setup looked almost trivial, more like a school demonstration than a challenge to Newton's legacy. But what mattered was not its appearance. It was the pattern that would emerge. As the light shone through the twin slits, Young observed the screen carefully, perhaps expecting to see two bright bands of illumination corresponding to the two paths the light should logically take. Instead, something far stranger unfolded. The light did not form two neat beams as a stream of particles might. It spread out and overlapped, producing a delicate series of alternating bright and dark bands, a pattern of interference, much like ripples in a pond colliding and reinforcing or canceling one another. This was the signature not of particles, but of waves. Just as water waves from two stones thrown into a still pool create an intricate pattern where their crests and troughs meet, so too did the light, invisible and weightless, behave as if it were a continuous wave, bending, interfering, and weaving with itself in a dance that defied the expectations of classical physics. Young repeated his observations again and again, refining the slits, adjusting distances, and using different sources of light to ensure the effect was not a trick of the eye. Each time, the same interference fringes appeared, their spacing predictable, their presence undeniable. In a paper presented to the Royal Society in 1803, he laid out his findings with calm precision, arguing that only a wave theory of light could explain what he had seen. It was a bold claim, and one that was not warmly received. Many of his contemporaries, steeped in Newton's authority, dismissed the idea as fanciful, even naive. Yet the evidence was there on the screen, plain to see, and no amount of skepticism could erase the elegant symmetry of those bright and dark fringes. What Young had uncovered was more than a curious optical effect. It was the first clear hint that the natural world was stranger and more subtle than anyone had imagined. Light, which had seemed so simple, now appeared capable of behaving like rippling water, spreading out, interfering, and forming patterns that no particle should produce. It was a revelation that would echo far beyond the confines of optics. Decades later, Augustin-Jean Fresnel in France would build upon Young's work, developing the mathematical theory of wave interference and further confirming that light was indeed a wave. And more than a century after that, in the early 20th century, the double-slit experiment would resurface in a new and even more unsettling context. As scientists like Albert Einstein, Louis de Broglie, and Niels Bohr discovered that electrons, the tiny particles thought to be the very building blocks of matter, could also produce interference patterns when passed through similar slits. The boundaries between wave and particle, once thought so clear, began to blur until they dissolved entirely. But on that quiet afternoon in 1801, none of this future complexity was yet known. There was only a darkened room, a flickering flame, and a man watching faint bands of light shimmer into being on a screen. The scene was humble, almost unremarkable, yet it marked a turning point in how humanity would come to understand the universe. What Young had shown, with the simplest of tools and the most patient of observations, was that the world was not built solely of solid, discrete things bouncing and colliding in predictable ways. Beneath the surface of everyday experience lay a subtler, more fluid reality, one that rippled and shifted and intertwined, obeying rules that defied common sense. And though it would take generations to grasp the full implications of that realization, the first whisper of quantum mystery, the idea that the universe might not move as we expect, had already begun to speak from the shadows of a London room. In the middle decades of the 19th century, the human world began to shrink, not because continents moved closer or ships suddenly sailed faster, but because ideas and messages, once bound to the speed of horses or the patience of sailing vessels, found a new path through the silent pulse of electricity. Until that moment, a letter from London to New York might take weeks, its ink fading slightly before it was ever read. And news of a political upheaval or a market crash often arrived long after it had ceased to matter. But in workshops scattered across Britain, Germany, and the United States, inventors and tinkerers stared at coils of copper wire and small glass insulators and wondered if thought itself could move faster, carried not by paper or breath, but by invisible currents racing through metal. It was out of this dream that the telegraph was born, a device so simple in its physical parts, a battery, a switch, a length of wire, and a receiver, yet so profound in its implications that it changed the tempo of civilization. When Samuel Morse sent the first official telegraph message on May 24, 1844, tapping out the words, "What hath God wrought from Washington, D.C. to Baltimore," it was more than a triumph of engineering. It was a quiet revolution. The clicks of the receiver were not sounds of steel or steam, but signals made of pure information, stripped of matter and moving at nearly the speed of light. Soon, a web of telegraph lines spread across nations like a new kind of nervous system, connecting cities and coasts, governments and markets. And yet the dream did not stop there, because the ocean's vast, cold, and indifferent, still separated continents. And the idea that a message might cross the Atlantic Ocean without waiting for a ship was a challenge too. Tempting to ignore the first attempt to stretch a telegraph cable beneath, the sea began in the 1850s. Led by an ambitious Irish-American entrepreneur named Cyrus Field, it was a colossal undertaking, a copper wire insulated with gutta percha, armored in iron and wound in massive coils aboard ships that laid it across. Nearly 2,000 miles of seabed between Valencia Island, Ireland, and Heart's Content, Newfoundland. When the first successful message, a greeting from Queen Victoria to President James Buchanan, arrived on August 20, 1858, it traveled across the ocean in just a few minutes, a feat that would have been considered magical a generation earlier. The cable failed weeks later, corroded and broken by the pressures of the deep. But the principle was proven, and by the 1860s, transatlantic telegraphy was a reliable thread binding the old and new worlds. For the first time, events in Europe could influence decisions in America within hours rather than weeks. And a political crisis, a commodity price, or a declaration of war could echo across oceans almost as soon as it occurred. while the telegraph transformed the world with wires. Another kind of revolution was quietly forming in the minds of scientists, who suspected that the wires themselves might not be necessary at all. The key lay in a set of equations published between 1861 and 1865 by the Scottish physicist James Clerk Maxwell, who brought together the separate forces of electricity and magnetism into a single framework. His four elegant equations revealed that changing electric fields could generate magnetic fields and vice versa. And together these shifting fields could travel through space as waves. In other words, space itself, empty, silent. Invisible space could carry signals, not as vibrations of air or tremors of metal, but as electromagnetic ripples moving at the speed of light. The idea was breathtaking, but proving it would take decades. It was not until 1887 that Heinrich Hertz demonstrated in his laboratory in Karlsruhe, Germany, that electromagnetic waves could indeed travel through air, reflecting off walls and sparking tiny receivers without the need for wires. Hertz's experiments were cautious, purely scientific in intent. But they confirmed Maxwell's bold prediction and opened the way for a new kind of communication, one that would leap free from the constraints of copper and cable. Among those who saw the potential was a young Italian named Guglielmo Marconi, who, in the 1890s, began building crude but ingenious transmitters capable of sending radio signals over increasing distances. In 1895, he achieved wireless communication over more than a kilometer in Bologna. By 1899, he had transmitted across the English Channel. Then, on a cold December day in 1901, Marconi staged a demonstration that captured the world's imagination from a station at Poldhu, Cornwall. He sent a signal consisting of 3 dots, the Morse code letter S, which was received on a kite-borne antenna in St. John's, Newfoundland, more than 3,000 kilometers away. Critics doubted that such a signal could curve with the Earth, yet it did, bouncing in ways no one yet understood. And with it, humanity had proven that messages could fly across oceans without a single strand of wire. The consequences of this discovery were enormous. Ships could now communicate across vast distances. Weather reports could travel between continents, and the rhythms of commerce, war, and daily life could synchronize as never before. The unseen world, once thought empty, was now alive with human thought encoded in invisible waves, humming silently through the air. It was a moment when the physical and the intangible truly merged, when space itself became a medium of communication, and when humanity first began to understand that information did not need a physical vessel to travel. The telegraph's sharp clicks and the radio's ghostly whispers were not just technological marvels. They were early signs of a deeper truth, that the universe itself, woven from fields and waves, is capable of carrying our voices, our ideas, and our imagination across the vast distances that once kept us apart. At the turn of the 20th century, in a city lit by gas lamps and the orange glow of iron foundries, a quiet but revolutionary idea was about to slip into the world, not with the loud triumph of a great discovery, but with the hesitant, almost reluctant steps of a scientist trying to solve what seemed a small, technical problem. In Berlin, 1900, the physicist Max Planck, then 52 years old and already well respected at the University of Berlin, was wrestling with a stubborn mystery that had haunted physicists for decades. Why objects glowed the way they did when heated, and why their light shifted from red to yellow to white as they grew hotter. This problem, known as the black body radiation problem, seemed simple on the surface. If you heated a piece of iron in a forge, it would glow a dull red, then orange, then white as the temperature climbed. Yet attempts to explain this behavior using classical physics always broke down, predicting absurd results including an ultraviolet catastrophe, an impossible explosion of energy at high frequencies that simply did not exist in reality. Planck was not seeking to overturn physics. He was, in his own words, trying to save it. In the late 1890s, he had devoted himself to understanding the mathematical form of black body. Radiation, the precise way the energy of emitted light, depended on its frequency and temperature. Experimental data from German physicists like Heinrich Rubens and Ferdinand Kerlbaum showed a clear pattern, but no existing theory could reproduce it. Planck tried everything he could think of, stretching the laws of thermodynamics and electromagnetism to their limits. The formulas refused to fit the facts. Finally, in desperation rather than inspiration, he made a strange and deeply uncomfortable assumption. Perhaps energy was not emitted in a smooth, continuous flow as everyone had believed, but instead indiscrete. Tiny packets, specific amounts that depended on the frequency of the light. On December 14, 1900, at a meeting of the German Physical Society, Planck presented his result. He had found that the energy E of each packet was proportional to the frequency F of the radiation. With a new fundamental constant of nature, H, linking them, E equals HF. The constant was astonishingly small, about 6.626 times 10^34 joule seconds, so small that its effects were invisible in the macroscopic world of engines, bridges, and planets. But in the realm of atoms and light, it changed everything. Planck called these packets quanta, using a Latin word meaning how much. He treated the concept as a mere mathematical trick, a temporary fix to match theory with observation. He could not yet imagine that this modest adjustment would become the cornerstone of a new physics. What Planck had stumbled upon was more than a clever solution to a nagging problem. It was a glimpse into a hidden structure of nature, a suggestion that energy long thought to flow like water from a faucet might instead come in drops. Indivisible and fundamental. The implications were enormous, though Planck himself did not pursue them. He was a cautious man, conservative in both temperament and science, and he viewed his quantum hypothesis with suspicion. Yet others saw its potential. Albert Einstein, in 1905, applied Planck's idea to explain the photoelectric effect, showing that light could knock electrons free from metal surfaces only if its packets were above a certain energy threshold. This was the first step toward understanding light not just as a wave, as Thomas Young and James Clerk Maxwell had described, but also as a stream of particles, photons, each carrying a quantum of energy. Planck's work also quietly united two great fields, thermodynamics and electromagnetism, and hinted at a deeper unity beneath them. The blackbody problem was, at its core, about how matter exchanges energy with radiation. And by introducing the idea of quantization, Planck suggested that the world of heat, light, and atomic motion might all obey the same fundamental rules. The smooth, continuous world of Newtonian mechanics, where energy could be divided endlessly, was giving way to a new landscape where nature operated in steps, not slides, and where the smallest scales of reality behaved according to rules that defied common sense. In the quiet lecture halls of Berlin, few realized that physics had just entered a new era. Newspapers did not report on Planck's presentation, and many of his peers regarded it as an obscure footnote in the study of thermal radiation. Yet in the decades that followed, this hesitant idea would grow into the foundation of quantum mechanics, shaping our understanding of atoms, molecules, stars, and the universe itself. Today, the constant H appears everywhere in the energy levels of hydrogen, the operation of lasers, the workings of transistors, and the glow of distant galaxies, a silent signature of that winter day in 1900, when the quantum first whispered its name. And so it was that a problem about glowing iron, a detail of laboratory physics, that might have seemed trivial, became the first breach in the wall of classical science. Through that breach came a new way of seeing the world, one in which certainty gave way to probability, continuity gave way to discreteness, and reality itself became something stranger and deeper than anyone had dared imagine. It was not a triumphant shout, but a quiet whisper. And yet that whisper would echo across the entire 20th century, shaping everything that followed at the dawn of the 20th century, when physics still seemed to rest on the solid foundations laid by Newton and Maxwell. A young patent clerk in Bern, Switzerland, began to question one of its most deeply held assumptions, the nature of light itself. His name was Albert Einstein, born in 1879 in Ulm, Germany. And though he was not yet the towering figure of scientific legend he would later become, his mind was already moving beyond the boundaries of conventional thought. In the year 1905, known now as his Annus Mirabilis, or Miracle Year, Einstein published 4 papers that transformed our understanding of space, time, matter, and energy. Among them, tucked between his groundbreaking work on relativity and Brownian motion, was a modest paper that would plant the seeds of one of the most revolutionary ideas in modern physics, the notion that light, long understood as a wave, could also behave as a particle. The puzzle Einstein sought to solve was known as the photoelectric effect, a phenomenon first observed in the late 19th century by scientists such as Heinrich Hertz and Wilhelm Hallwachs. They had noticed that when ultraviolet light struck a metal surface, electrons were ejected from it, producing a measurable electric current. The effect was puzzling because it did not behave as wave theory predicted. According to classical physics, increasing the brightness of light, and therefore its energy, should have increased the energy of the emitted electrons. But experiments showed otherwise. Even the most intense light failed to knock electrons loose if its frequency was too low, while even faint light at higher frequencies could do so instantly. The inconsistency hinted at a deeper truth hidden beneath the wave. Description of light: Einstein's solution was as bold as it was unsettling. Drawing on Max Planck's recent work on blackbody radiation, he proposed that light was not emitted in a continuous wave, but rather in discrete packets of energy, which he called quanta. Each packet carried an energy E equals hf, where h was Planck's constant and f the frequency of the light. When one of these packets struck a metal surface, it transferred its energy to an electron. If the quantum's energy exceeded the electron's binding energy, the work function of the metal, the electron would be ejected. The intensity of the light, Einstein explained, affected the number of electrons released, but not their energy. That depended solely on the frequency of the individual quanta. This was a radical departure from accepted theory. Light had been conclusively shown to behave as a wave. Thomas Young's double-slit experiment in 1801 and James Clerk Maxwell's electromagnetic theory in the 1860s had cemented that view, and now Einstein was suggesting it also behaved like a particle. The dual nature of light was deeply counterintuitive, and many physicists resisted the idea. Even Planck himself, whose work had inspired Einstein's insight, initially regarded the notion of light quanta as an unnecessary complication. Yet experiment after experiment confirmed Einstein's explanation, and the strange, particle-like behavior of light could no longer be ignored. The photoelectric effect was more than an intellectual curiosity. It revealed a direct, measurable link between light and electricity, a relationship that would eventually shape the technological world. Modern solar panels, which convert sunlight into electrical current, operate on precisely this principle. When photons, the modern name for Einstein's quanta of light, strike a semiconductor material, they liberate electrons, generating a flow of current that can power homes, cities, and even spacecraft. The same fundamental process underlies countless devices, from photodiodes in cameras to sensors in scientific instruments, each a quiet descendant of the experiments that puzzled physicists more than a century ago. Einstein's paper on the photoelectric effect did not attract widespread attention at first. It was one of several revolutionary ideas he published that year, and its implications took time to sink in. But as quantum theory developed in the 1910s and 1920s, with contributions from Niels Bohr, Louis de Broglie, and Werner Heisenberg, the concept of light quanta became a central pillar of the new physics. In 1921, the Nobel Committee awarded Einstein the Nobel Prize in Physics, not for his theories of relativity, which were still considered too controversial, but specifically for his explanation of the photoelectric effect, recognizing it as a discovery that had fundamentally altered our understanding of the physical world. The deeper significance of Einstein's insight lay not just in the behavior of light, but in what it revealed about nature itself. It suggested that the universe, at its most fundamental level, was granular, that energy, like matter, came in indivisible units. This idea, unsettling though it was, hinted at a deeper unity between particles and waves, matter and energy, that physicists would spend decades unraveling. It was a crucial step on the path to quantum mechanics, a theory that would eventually explain the structure of atoms, the behavior of semiconductors, and even the fusion reactions that power the stars. And so, in a quiet office above a patent office in Bern in 1905, a young man with no laboratory and few resources proposed an idea that overturned centuries of certainty. He showed that light could behave not just as a continuous wave, but as a stream of particles, carrying a tiny but precise quantum of energy. That insight not only solved a stubborn experimental puzzle, but also transformed the way we think about the universe, laying the foundation for technologies that shape our lives and for a physics that still, more than a century later, continues to reveal new layers of reality. What began as a modest attempt to explain why light could free electrons from metal surfaces became one of the most profound revolutions in science. Proof that even the most ordinary phenomena can, when looked at closely enough, whisper truths that change everything. In the years following Einstein's proposal that light itself could behave like a particle, a new and even stranger question began to form in the minds of physicists. If light, which had long been regarded as a wave, could also act like a particle, then might the reverse also be true? Could matter itself, the very stuff of the physical world, sometimes behave like a wave? The man who gave voice to this daring thought was Louis de Broglie, a French aristocrat and physicist born in 1892, who came of age in the shadow of the First World War and found in the quiet of libraries and lecture halls a refuge from the turmoil of his time. In his 1924 doctoral thesis at the University of Paris, de Broglie proposed with calm audacity that every particle of matter, no matter how small or large, might carry with it a wavelength, an intrinsic wave nature tied to its momentum by the simple relation lambda equals hp, where h was Planck's constant and p the particle's momentum to most of his contemporaries. The suggestion seemed absurd. Matter was tangible, solid, and measurable. And to speak of it as a wave sounded like a return to medieval speculation rather than progress in modern science. Yet de Broglie's argument had a compelling elegance. If photons, once thought purely waves, could show particle-like behavior, then perhaps electrons, long assumed to be tiny corpuscles of charge, might reveal wave-like features under the right conditions. Albert Einstein himself, already a Nobel laureate and one of the most respected minds in physics, read de Broglie's thesis and declared that the idea held promise. With Einstein's support, de Broglie's notion of matter waves entered the growing conversation of quantum theory. Though it remained to be proven in the laboratory, the proof arrived only a few years later in an unlikely setting. The Bell Telephone Laboratories in New York, where two American physicists, Clinton Davison and Lester Germer, were studying how electrons scattered from the surface of a nickel crystal. Their original intent in the mid-1920s had been practical, linked to improving vacuum tubes for telecommunication systems. But an accident in their experimental setup led to an unexpected revelation. In 1925, when their nickel surface was accidentally oxidized and then heated to restore it, the crystal formed a more regular structure. And when a beam of electrons struck this surface at certain angles, the scattered intensity showed clear peaks and troughs, precisely the kind of interference pattern one would expect from waves diffracting around a grating. It was a moment of quiet astonishment. Here were electrons, the very archetype of a particle, leaving behind the unmistakable signature of a wave. The hum of vacuum pumps, the faint glow of electron beams inside glass chambers, the clicking of instruments had, without warning, confirmed one of the boldest ideas in physics. Davison and Germer published their findings in 1927. And almost simultaneously, George Paget Thomson, in Britain, son of J.J. Thomson, the discoverer of the electron, demonstrated similar results by passing electrons through thin metal foils. Together, these experiments showed that de Broglie's matter waves were not speculation but fact, and that the strange new quantum theory was not a passing curiosity, but a doorway into an entirely new view of reality. The implications were staggering. If electrons could behave like waves, then atoms themselves could be understood in a new way. Only a few years earlier, Niels Bohr had proposed his model of the hydrogen atom, with electrons orbiting the nucleus like planets around the sun, but his theory required awkward assumptions to explain why electrons occupied only certain orbits. De Broglie's waves provided the missing piece. Electrons could only exist in orbits, where their wave crests and troughs fit neatly around the nucleus, reinforcing themselves like standing waves on a violin string. This wave condition explained the stability of atoms and the discrete energy levels observed in their spectra, weaving quantum mechanics into the very fabric of matter in the dim light of those early laboratories. With glass tubes hissing softly and oscilloscopes tracing faint lines across phosphor screens, the world had been forced to accept a new kind of duality. Electrons, once thought of as indivisible particles, were also waves, and their ghostly paths could only be described in terms of probabilities and interference, not certainties. This dual nature, unveiled by de Broglie's imagination and confirmed by de Broglie's and Germer's patience, was the next step in the unfolding mystery of quantum physics. It was proof that the universe did not move in the straightforward, mechanical way once imagined, but along ghost paths unseen. Wavering and deeply strange, humming quietly in the laboratories where the future of science was being born. In the years following Einstein's daring proposal that light could behave as a particle, the scientific world found itself standing on ground that no longer felt as firm as it once had. The boundaries that had seemed so clear, waves belonged to water and sound. Particles belonged to matter, were now blurred by the unsettling suggestion that even light itself, that most familiar and ancient of phenomena, could exist in both forms depending on how one looked at it. Yet if light, once considered the purest wave, could also act as a particle, then an even more audacious question soon followed. Could matter, the solid stuff of the universe, behave as a wave too? It was Louis de Broglie, a French aristocrat turned physicist born in 1892, who first had the courage to say yes in 1924. While working on his doctoral thesis at the University of Paris, de Broglie proposed something that at the time sounded more like philosophy than physics. Building on Einstein's idea that light could be both wave and particle, he reversed the logic and suggested that particles, electrons, protons, even entire atoms might also possess wave-like properties. His reasoning was simple, yet profound. If light, once thought to be a continuous wave, could behave as discrete quanta with momentum, then perhaps electrons, long treated as indivisible particles, might also have a wavelength associated with their motion. He even wrote down an expression for this wave, relating its wavelength lambda day, 2 Planck's constant h, and the particle's momentum p, lambda equals frac hp. This was more than mathematical curiosity. It was a direct challenge to centuries of thinking. Matter was supposed to be solid, tangible, definite. The notion that it could stretch and bend like a wave was almost unthinkable. Yet de Broglie's arguments were so elegant and so consistent with the emerging quantum picture that Albert Einstein himself supported the idea, writing that it revealed a new way of thinking about nature. The real test, however, was not philosophical but experimental. A theory, no matter how beautiful, must be proven in the laboratory, and the chance to do so came just a few years later in a quiet basement laboratory at Bell Telephone Laboratories in New York. There, in 1927, 2 American physicists, Clinton Davison and Lester Germer, were investigating how electrons scattered off the surface of a nickel crystal. Their initial work had nothing to do with de Broglie's hypothesis. They were studying surface properties to improve vacuum tubes. But a fortunate accident changed everything. One day, a small explosion in their vacuum system oxidized the nickel surface, forcing them to heat it and recrystallize it before continuing. The newly ordered crystal acted not as a random scatterer, but as a diffraction grating, and when they fired a beam of electrons at it, the resulting pattern was not what one would expect from tiny billiard balls colliding with a wall. Instead, they observed a series of bright and dark bands, an interference pattern, the unmistakable fingerprint of wave behavior. This result, published in 1927, was astonishing. It confirmed de Broglie's prediction with precision. The measured wavelengths of the electrons matched, the values calculated from their momentum using his formula. Suddenly, matter itself, the electrons that carried current through wires, the building blocks of atoms, was behaving like light in Thomas Young's double-slit experiment of 1801. Particles were no longer mere points in space. They were also waves, spread out and capable of interfering with themselves. The implications were staggering. The classical picture of matter as hard, localized objects was gone, replaced by a subtler, more elusive reality in which particles were described by wave-like probabilities rather than fixed positions. This shift would soon become the foundation of quantum mechanics, especially in the work of Erwin Schrödinger, who, in 1926, built on de Broglie's insight to develop his wave equation, a mathematical framework describing how these matter waves evolve over time. The familiar orbiting electrons of Niels Bohr's early atomic model gave way to clouds of probability, regions where electrons were likely to be found, and the atom itself became a shimmering, dynamic structure rather than a miniature solar system. In the laboratories where these discoveries unfolded, the atmosphere was not one of triumphant revelation, but of quiet astonishment. Vacuum pumps hummed steadily, electron guns glowed faintly, phosphorescent screens lit up with patterns no one had expected to see. Men and women in white coats stared at lines and dots that defied every textbook they had studied. And though the mathematics could explain the results, the deeper meaning remained elusive. How could a single electron, fired one at a time through a slit, interfere with itself to form a wave pattern? How could something so small and solid act as if it were spread out across space? These were not questions that could be answered quickly, and nearly a century later. They still haunt physicists. Yet from that quiet hum of equipment and that faint green glow on a laboratory screen emerged a truth that would change our view of reality forever. Matter, it turned out, was not what it seemed. It was not rigid or sharply defined, but fluid and probabilistic, capable of behaviors that belonged as much to waves as to particles. The universe, once imagined as a clockwork of discrete, predictable pieces, was instead a vast sea of ghostly waveforms, overlapping, interfering, and shaping everything we see. And all of it, the entire strange quantum vision of the world, began with a single, daring idea from a young French physicist and a beam of electrons that refused to behave as expected. In the late 1920s, as the glow of gas lamps spilled across the cobbled streets of Copenhagen, the world of physics found itself in a state of exhilarating confusion. The discoveries of the previous 2 decades, Max Planck's quanta, Albert Einstein's photons, Louis de Broglie's matter waves, and the strange interference patterns observed by Clinton Davison and Lester Germer, revealed a universe far stranger and less certain than the one Isaac Newton had described 2 centuries before. The task now was not simply to uncover more experimental facts, but to understand what they meant, and it was here, in the quiet rooms of the Institute for Theoretical Physics, founded by Niels Bohr in 1921, that the deepest and most enduring debates of the new science would unfold. The Institute was not a grand palace of marble and steel, but a modest building filled with chalkboards, scrawled over with equations, cigarette smoke curling toward the ceiling, in the low hum of conversation in a half-dozen languages. It became a kind of pilgrimage site for young physicists from around the world, all drawn by Bohr's reputation for deep thought and careful reasoning. Bohr himself, born in 1885 in Copenhagen, had already transformed physics with his model of the atom in 1913, showing that electrons orbited nuclei in discrete energy levels rather than in classical paths. But by the late 1920s, that model, though revolutionary in its time, was beginning to show its limits, and the deeper nature of quantum mechanics demanded new ways of thinking. It was during these years that Bohr was joined by a brilliant and ambitious young German physicist named Werner Heisenberg. Born in 1901, whose sharp intellect and fearless approach to the unknown made him one of the most promising minds of his generation. In 1925, Heisenberg had introduced a radically new formulation of quantum theory known as matrix mechanics, which dispensed with familiar concepts like orbits and trajectories and instead described particles using arrays of numbers. presenting their observable properties. Around the same time, Erwin Schrödinger and Zurich developed wave mechanics, a more intuitive but equally abstract approach that treated particles as wave-like entities spread through space. Both methods produced the same predictions, and together they formed the mathematical backbone of quantum physics. Yet neither explained what those equations actually meant. This question, the question of interpretation, consumed the conversations that unfolded late into the night in Bohr's Institute. Over cups of strong coffee and under the soft flicker of candlelight, Bohr and Heisenberg argued about the nature of reality itself. Heisenberg, struggling to make sense of the equations he had written, came to a startling conclusion in 1927. It was not possible to know both the position and the momentum of a particle with perfect precision at the same time. The more precisely one was measured, the more uncertain the other became. This was not a flaw of instruments or a limitation of technology. It was a fundamental property of nature itself. Heisenberg expressed this idea in what became known as the uncertainty principle, and it struck at the heart of classical physics, which had always assumed that the universe could, at least in theory, be described in exact detail. Bohr embraced this uncertainty, but he took the idea even further. He argued that the very act of measurement was inseparable from the reality being measured. In his view, particles did not have definite properties until they were observed. Their behavior was governed not by fixed laws but by probabilities described by Schrödinger's wave function. This interpretation, which came to be known as the Copenhagen interpretation, suggested that quantum mechanics did not reveal how things are, but only how they might be until an observation forced nature to choose reality. In other words, it was not something that existed independently of us. It was something that emerged through interaction. Not everyone agreed. Albert Einstein, though one of the pioneers of quantum theory, was deeply troubled by the implications of Bohr's view. He famously objected, "God does not play dice," rejecting the idea that the universe was governed by chance. Bohr, in turn, responded gently but firmly, "Stop telling God what to do." Their debates, which began in 1927 at the Fifth Solvay Conference in Brussels and continued for years, were not mere academic disagreements. They were philosophical storms. Grappling with the most fundamental questions about the nature of reality, was the universe deterministic or probabilistic? Did particles exist when they were not observed? Was quantum mechanics a complete description of nature, or did it hide deeper truths yet to be found? For Heisenberg and Bohr, the answers lay not in certainty, but in humility. The universe, they argued, might not yield its secrets in the language of classical logic. Instead, it required a new vocabulary, one of probabilities, complementarities, and dualities, to describe phenomena that refused to fit into familiar categories. An electron could be both wave and particle, depending on how one looked at it. A quantum system could exist in many possible states at once, collapsing into a single outcome only when measured. And reality itself might not be a fixed objective stage on which events unfold, but a dynamic process shaped by interaction and observation. Those late-night discussions in Copenhagen, illuminated by the soft glow of oil lamps and chalk dust drifting through the air, did more than shape the interpretation of quantum mechanics. They transformed the very way we think about the universe. They forced humanity to confront the unsettling idea that knowledge has limits, that nature is not a clockwork machine, but a tapestry woven from probabilities, and that our role as observers is not peripheral, but essential. The debates were often heated, sometimes deeply personal, and never fully resolved. But they gave rise to a framework that, despite its strangeness, has withstood every experimental test for nearly a century. And so, in those smoky rooms and whispered conversations, the foundations of modern physics were laid, not as a set of final answers, but as an invitation to keep questioning what real truly means. In the autumn of 1935, as the streets of Vienna filled with the rattle of tramcars and the distant tolling of church bells, one of the most unsettling ideas in the history of science was quietly taking shape inside a modest apartment lined with books and papers. Erwin Schrödinger, the Austrian physicist who had given the world the mathematical wave equation that described the strange behavior of quantum particles, was deeply dissatisfied with how his work was being interpreted. The wave function he had devised in 1926 was meant to describe how particles like electrons moved and interacted, yet its implications, embraced by Niels Bohr and Werner Heisenberg in Copenhagen, suggested something far more radical: that particles could exist in many possible states at once, a condition known as superposition, and that these possibilities did not become real until someone or something observed them. To Schrödinger, this was not just counterintuitive, it bordered on the absurd. To expose what he saw as a flaw in the Copenhagen interpretation, Schrödinger proposed a story, not an equation. A thought experiment that would drag the invisible weirdness of quantum theory into the everyday world where common sense was supposed to rule. He imagined a sealed box, one that could not be opened or peeked into without disturbing what was inside. Into that box, he placed 3 components: a living cat, a tiny vial of poisonous gas, and a radioactive atom connected to a trigger mechanism. The setup was simple. If the atom decayed, a random quantum event that, according to theory, could only be described by probabilities, it would release the poison and kill the cat. If it did not decay, the cat would remain alive. The crucial detail was this: according to quantum mechanics, until an observation was made, the atom existed in a superposition of decayed and undecayed states simultaneously. And if the fate of the cat depended on the state of the atom, then, by extension, the cat too must exist in a superposition, alive and dead at the same time, till someone opened the box and looked. It was a deliberately unsettling image, even macabre, but that was precisely Schrödinger's point. He wanted to show that if the Copenhagen interpretation were taken at face value, its consequences extended beyond the subatomic realm and into the familiar world of everyday objects. A cat, he argued, could not be both alive and dead. Common sense demanded that it be one or the other, regardless of whether anyone was watching. Yet the mathematics of quantum theory, which had so accurately predicted countless experiments, said otherwise. It said that reality did not choose a single outcome until observation forced it to. The thought experiment, first published in November 1935 in a paper titled Die Gegenwärtige Situation in der Quantenmechanik, the present situation in quantum mechanics, quickly became the most famous paradox in modern physics. It was not meant as a literal proposal. Schrödinger had no intention of putting a cat through such an ordeal, but as a way to dramatize the profound strangeness of quantum mechanics when extended beyond the microscopic world, and it worked. Physicists and philosophers alike were forced to confront the uncomfortable question it raised. If quantum rules apply to electrons and atoms, why shouldn't they also apply to larger systems? Where exactly does the quantum world end and the classical world begin? And what role does observation, or perhaps consciousness itself, play in determining what is real? These questions sparked fierce debate that continues to this day. Bohr maintained that Schrödinger's scenario did not undermine quantum theory, but rather illustrated its essence. The cat's dual state, he argued, was not a physical reality, but a description of our knowledge, or lack of it, about the system before measurement. In this view, the wave function does not describe a physical superposition of life and death, but a mathematical catalog of possibilities that collapses into a single outcome when observed. Albert Einstein, on the other hand, seized on the thought experiment as further evidence that quantum mechanics was incomplete. He famously quipped that he preferred to believe the moon was still there, even when no one was looking at it, implying that reality must exist independently of observation, despite Schrödinger's intentions. The cat paradox did not discredit the Copenhagen interpretation. If anything, it made it more famous. It highlighted, in the simplest and most haunting terms, the central mystery of quantum mechanics, that the act of observation does not merely reveal what is already there, but appears to play a role in bringing it into being. In the decades that followed, experiments with photons, electrons, and even molecules confirmed that superposition is not just a mathematical trick, but a real physical phenomenon. Particles fired one at a time through a double slit still interfere with themselves, as if they travel along multiple paths simultaneously. until a detector is placed to watch them, at which point the interference vanishes. And they behave like classical particles. The Katina box remains a metaphor that refuses to fade, precisely because it captures something so deeply unsettling about the universe. It suggests that reality is not a fixed stage upon which events unfold, but a fluid, shifting tapestry woven from probabilities, collapsing into the tangible world only when we interact with it. It forces us to accept that what we see as solid and certain might, beneath the surface, be something more ghostly and indeterminate. And it reminds us that the simple act of looking something as ordinary as opening a box might not just reveal reality, but help create it. In that quiet Vienna apartment in 1935, with papers stacked high and chalkboards filled with equations, Schrödinger set a paradox loose into the world, one that continues to haunt science, philosophy, and imagination alike. A question that refuses to stay locked in its box in the early decades of the 20th century. When the foundations of physics were being shaken and rebuilt in ways that would have seemed impossible a generation earlier, there was one gathering that came to symbolize both the brilliance and the uncertainty of the age. It was known simply as the Solvay Conference, a meeting of minds that brought together the greatest scientific thinkers of their time. Not in crowded lecture halls or noisy laboratories, but in elegant European settings, where marble staircases and oil paintings of long-dead kings seemed to watch silently as the future of science was debated below. The first of these meetings was held in Brussels in 1911. Organized by the Belgian industrialist Ernest Solvay, who had made his fortune in the chemical industry and believed that supporting science was one of the best ways to give something back to the world. He invited the brightest physicists and chemists to come together and discuss the most urgent questions of their fields. And though the early conferences focused on radiation and the structure of matter, it was the fifth Solvay meeting in October 1927 that would become legendary. The moment when the emerging quantum theory faced its greatest philosophical reckoning. The setting was as far from a laboratory as one could imagine. Black-coated physicists, many of them still in their 30s, walked beneath chandeliers and stood in small clusters beneath frescoed ceilings, their conversations drifting between German, French, and English. They posed for photographs on the steps of the Hotel Metropole, some smiling awkwardly, others staring into the camera with the solemnity of men who knew they were standing at the edge of something enormous. In one of those photographs, now famous and endlessly reproduced in textbooks, 29 figures stare out from the past. 17 of them were, or would become, Nobel laureates. Among them were Albert Einstein, Niels Bohr, Marie Curie, Werner Heisenberg, Erwin Schrödinger, Max Planck, and Paul Dirac, a constellation of intellects rarely, if ever, assembled in one place before or since. It is said that when a young physicist walked into the room for the first time, he whispered that it felt as if every equation that mattered had suddenly taken human form. But the Solvay Conference was never about polite conversation or ceremonial recognition. It was a battlefield, not of armies or weapons, but of ideas. And the fiercest battle of all was waged between two men whose respect for one another was as deep as their disagreements were irreconcilable. Einstein, by then already the most famous scientist in the world, and a figure whose name had become synonymous with genius, had grown increasingly uneasy with the direction quantum theory was taking. The new physics, with its probabilities and uncertainties, its refusal to offer a clear picture of reality beneath the mathematics, offended his deeply held belief that the universe must be orderly and comprehensible. Bohr, quieter in demeanor but just as determined, believed that quantum mechanics was complete as it stood, that nature itself was not obliged to conform to human expectations of clarity and determinism. The debates between them were intense and unrelenting, often stretching late into the night and continuing over coffee the next morning. Einstein would present one thought experiment after another, scenarios designed to expose what he saw as the contradictions or incompleteness of quantum mechanics. Bohr, patient and meticulous, would counter each one, showing that the mathematics still held, that the uncertainty principle and the wave function were not weaknesses, but essential features of a deeper reality. On one occasion, Einstein famously declared that God does not play dice with the universe, a metaphor for his refusal to accept that chance and probability were fundamental to nature. Bohr, in his characteristically gentle way, replied, "Stop telling God what to do." The remark was delivered without malice, but it captured the essence of their philosophical divide. Einstein's belief in an underlying determinism versus Bohr's conviction that nature was inherently indeterminate until observed. Yet despite the intensity of their arguments, the atmosphere of the Solvay meetings was not one of bitterness or hostility. There was laughter, too quiet, knowing laughter among people who understood that they were participating in something larger than themselves. There were walks through the tree-lined streets of Brussels, shared dinners at long tables where conversation flowed as freely as the wine, in moments when even the most heated rivals would stand side by side, gazing at a blackboard and nodding in silent agreement over a difficult calculation. These were men and women of towering intellect, but they were also human beings, with doubts, vanities, and flashes of humor. Marie Curie, one of the few women present, sat with her usual calm amid the storm of debate, offering occasional insights that cut through the noise. Heisenberg, still in his 20s, sometimes listened more than he spoke, absorbing the wisdom of those who had paved the way for his own discoveries. The legacy of those meetings was not a definitive answer to the mysteries of quantum mechanics. The questions that burned so fiercely in 1927 about determinism, reality, and the role of observation remain unresolved even today. But the Solvay Conference achieved something arguably more important. It created a space where science could be both rigorous and profoundly human, where disagreement did not fracture collaboration, and where even the most abstract ideas were debated face-to-face by the people who had conceived them. It was a reminder that discovery is not just about equations written on chalkboards, but about the conversations, arguments, and shared moments that shape how those equations are understood. When we look at the faded group photograph now, nearly a century later, it is tempting to see only the monumental figures and the epic-changing discoveries they represent. But behind each face lies a story of late-night arguments in smoky rooms, of laughter echoing through marble halls, of fragile egos and deep respect. The palace that hosted them was not just a venue for science, it was a stage for one of the most remarkable human dramas ever played out in the history of ideas. And in that drama, the universe itself seemed to lean closer, waiting to see what these extraordinary minds would decide it was made of by the early 1930s. The once solid picture of the atom, a tiny solar system of electrons circling a compact nucleus, had begun to feel more like a shadow than a structure. The deeper scientists peered into matter, the more elusive its secrets became, the more it seemed that the atom was not a final building, its block, but a doorway into something far stranger and more complicated. The breakthroughs of the previous decades, Ernest Rutherford's discovery of the nucleus in 1911, Niels Bohr's model of atomic orbits in 1913, and James Chadwick's confirmation of the neutron in 1932, had transformed our understanding of the microscopic world, but they had also revealed how much was still unknown. The nucleus, dense and tiny beyond comprehension, contained nearly all of the atom's mass, and yet how its components behaved and how they interacted with one another remained hidden behind a veil that ordinary observation could not penetrate. If scientists were to go further, they would need new tools, tools capable of tearing open the invisible and forcing it to reveal what lay inside. The key to that next step was not a microscope or a telescope, but a machine built not to look at nature gently, but to strike it with unimaginable force. It was called the cyclotron, a device invented in 1930 by a young American physicist named Ernest O. Lawrence at the University of California, Berkeley, where earlier experiments had relied on naturally occurring radioactive particles or the modest energies of simple vacuum tubes. Lawrence's machine used powerful magnetic fields and carefully timed electric pulses to accelerate charged particles to tremendous speeds. The concept was surprisingly simple. Particles such as protons would spiral outward through a magnetic field, gaining energy with each pass until they reached velocities high enough to smash into atomic nuclei and break them apart. The first cyclotron was small enough to hold in one hand a brass glass, its device only about 4 inches across, but it opened a new era in experimental physics. Within a few years, Lawrence and his team were building larger versions, some more than a meter in diameter, capable of accelerating particles to energies millions of times, greater than those in chemical reactions. When those particles struck their targets, they did something that nature rarely allowed. They split the nucleus open and revealed its inner workings. In 1932, just as the first cyclotrons were being refined, James Chadwick in Cambridge confirmed the existence of the neutron, a neutral particle with a mass nearly identical to that of the proton. Its discovery solved a lingering puzzle: why atomic masses were greater than the number of protons alone would suggest, and it offered a new kind of projectile for nuclear experiments, one unimpeded by the electrical repulsion that deflected charged particles. Neutrons could slip past the positive charge of the nucleus and strike its heart directly, triggering reactions that released vast amounts of energy or created entirely new elements. In laboratories from Berkeley to Cambridge, the air was alive with a mixture of excitement and disbelief as these machines began to uncover a hidden menagerie of subatomic entities. Collisions produced strange byproducts that hinted at new forces and new particles, fleeting visitors like the positron. Discovered by Carl Anderson in 1932, the muon a few years later, and other exotic species that defied the NEAT. Simple models of the atom that had seemed so solid only a generation earlier, each new particle added another layer to the story, forcing physicists to revise their theories and admit that the nucleus was not a simple assembly of protons and neutrons, but a dynamic, complex system governed by forces that operated on scales smaller and stranger than anyone had imagined. The experiments themselves were feats of both engineering and patience. The cyclotrons roared and hummed in their underground chambers, surrounded by heavy lead shielding and humming vacuum pumps. Technicians in lab coats adjusted dials and watched meters while physicists sketched reaction pathways on chalkboards and argued over the meaning of the data pouring from their detectors. The collisions themselves were over in trillionths of a second, but their consequences were recorded in the delicate tracks left in photographic plates or the sudden clicks of Geiger counters. What had once been invisible was now not only visible, but measurable, and each measurement chipped away at the old certainties, replacing them with a new understanding of matter as a web of interactions rather than a collection of simple parts. These discoveries did more than expand scientific knowledge. They transformed the world itself. The realization that splitting nuclei could release immense quantities of energy, hinted at by Albert Einstein's equation E=mc(A), would soon lead to the development of nuclear reactors and euclear reactors, more ominously atomic weapons. But in those early years, before the full implications were understood, the work was driven by something simpler and purer: curiosity. Physicists wanted to know what the universe was made of and how its smallest pieces behaved. The machines they built were not weapons, but questions made tangible. Instruments designed to push against the boundaries of the known and see what pushed back. By the late 1930s, the picture of the atom had changed beyond recognition. It was no longer a miniature solar system or a static nucleus surrounded by orbiting electrons. It was a teeming, restless landscape of particles and forces, a place where collisions created new forms of matter and where even the most fundamental building blocks could be split and transformed. The invisible world, once silent and still, it had begun to speak, and it spoke in the language of high-energy impacts, in the spiraling traces of subatomic debris, and in the deepening understanding that nature's smallest scales were far richer and stranger than anyone had dared to imagine. The cyclotron's roar, echoing from the basements of Berkeley and beyond, was more than the sound of a machine. It was the heartbeat of a new science, one that would reshape our understanding of matter, energy, and the universe itself. By the time the 1930s gave way to the 1940s, quantum theory had already transformed physics from a study of visible predictable forces into a science of probabilities, particles, and hidden structures. But it was the brutal urgency of World War II that forced many of those discoveries out of the realm of theory and into the world of machines, weapons, and geopolitics. The war, which began in September 1939 with Germany's invasion of Poland and quickly spread into a global conflict, demanded new ways of seeing, new ways of communicating, and new ways of harnessing the energy locked inside matter itself. Quantum physics, once the domain of university lecture halls and chalkboard debates, was about to become the engine that powered some of the most consequential technologies of the 20th century. And in the process, it would blur forever the line between scientific wonder and destructive potential. Even before the war officially began, governments had begun quietly recruiting physicists to tackle urgent technological problems, many of them rooted in quantum principles. In Britain and the United States, radar, a technology based on the emission and reflection of electromagnetic waves, was rapidly becoming essential for detecting enemy aircraft and submarines. The first experimental radar systems was tested in the mid-1930s by scientists such as Sir Robert Watson-Watt in the United Kingdom. Relied on the careful manipulation of radio waves and the quantum understanding of how electrons behave in vacuum tubes. By 1940, radar stations dotted the British coastline, their spinning antennas scanning the skies for German bombers, and their success in the Battle of Britain proved that quantum physics was not just an abstract curiosity, but a matter of national survival. But the most dramatic application of quantum theory during the war would take place not on windswept coastal cliffs, but in a remote, high-security laboratory deep in the desert of New Mexico. In 1942, under the direction of the American physicist J. Robert Oppenheimer and with support from the newly formed Manhattan Engineer District, a team of scientists gathered at a hastily constructed research center known simply as Los Alamos. Their mission, codenamed the Manhattan Project, was to unlock the enormous energy hidden within the atomic nucleus, a feat that could only be understood through the quantum principles developed in the first decades of the century. The work drew on discoveries stretching back to Ernest Rutherford's experiments with nuclear transmutation in 1919, James Chadwick's identification of the neutron in 1932, and the realization, inspired by Albert Einstein's equation E=mc(A), that mass and energy were interchangeable. The project brought together some of the most brilliant minds of the era: Niels Bohr, Enrico Fermi, Hans Bethe, Richard Feynman, and many others, each contributing a piece of the puzzle. At its heart was the challenge of understanding and controlling nuclear fission, the process by which a heavy atomic nucleus splits into smaller fragments, releasing vast amounts of energy and additional neutrons in the process. The mathematics of neutron behavior, the probabilities of chain reactions, the design of bomb cores, all depended on quantum mechanics. Even the enrichment of uranium-235 and the production of plutonium-239, the fissile materials required for a bomb, involved techniques rooted in quantum physics, from isotope separation, based on subtle mass differences, to the neutron capture reactions inside nuclear reactors. Life at loss. Alamos was a strange blend of intense scientific collaboration and military secrecy. Chalkboards were filled with equations describing neutron diffusion and cross-sections, while heavily guarded warehouses stored the precious materials required for the weapon. The scientists, many of whom had devoted their lives to pure research, now found themselves calculating critical masses and blast yields. Knowing that their work could level cities, some, like Oppenheimer, felt a deep sense of responsibility and unease. Others believed that defeating Nazi Germany, which they feared might be pursuing its own atomic program under Werner Heisenberg, justified any cost. In July 1945, at a site called Trinity near Alamogordo, New Mexico, those calculations were put to the ultimate test. The world's first nuclear device, a plutonium implosion bomb, was detonated with a blinding flash that turned night into day and released an energy equivalent to 20,000 tons of TNT. Oppenheimer, recalling a line from the Bhagavad Gita, whispered, "Now I am become death, the destroyer of worlds." Quantum theory's influence on the war extended beyond the bomb. Advances in quantum electronics paved the way for improved communication systems, cryptographic devices, and even the first steps toward computing. Physicists working in radar research laid the groundwork for microwave technology, which would later find peaceful uses in medicine and telecommunications. The same understanding of atomic structure that enabled nuclear weapons also led to the development of nuclear reactors, which by 1943 were already being considered as sources of power for submarines and future energy generation. Yet beneath the triumph of these achievements ran a current of discomfort that many of the scientists involved never fully escaped. The very theories born from curiosity about the nature of light and matter, theories that had once seemed to belong to a realm of pure thought, had now been used to destroy cities, as they were at Hiroshima and Nagasaki in August 1945. The uneasy marriage of wonder and weaponry had reshaped the world's political landscape and inaugurated a nuclear age that would define the second half of the 20th century. For many, it was a sobering reminder that knowledge, once gained, cannot be contained, and that the power to understand nature often comes with the power to reshape or destroy it. In the end, the war left quantum physics forever changed. It was no longer an esoteric pursuit confined to laboratories and conferences. It had become a force that shaped history, politics, and the fate of nations. The equations scribbled on blackboards in the 1920s had become blueprints for radar arrays and atomic bombs, and the scientists who once debated uncertainty and superposition in lecture halls now wrestled with the moral uncertainties of their own creations. Out of that tension between wonder and fear, curiosity and responsibility, the modern world was born, and quantum theory stood at its center. A reminder that even the most abstract ideas can cast the longest shadows in the years immediately following the Second World War. As the world adjusted to a new geopolitical reality and physicists wrestled with the consequences of their wartime discoveries, another frontier of quantum science was quietly opening in places far removed from bomb labs and radar stations. It was not a field defined by explosions or heat, but by silence and cold. By laboratories where the air was so still that the ticking of a clock seemed loud, and where temperatures plunged to within a fraction of a degree above absolute zero. It was in these icy chambers that some of the most astonishing behaviors of matter would reveal themselves. Behaviors that defied the expectations of classical physics and exposed, once again, how deeply quantum mechanics govern the universe beneath the surface of everyday experience. The story began decades earlier. In 1908, when the Dutch physicist Huyck Kamerlingh, working at the University of Leiden, first succeeded in liquefying helium. This was no small feat. Helium remains a gas until cooled below 4.2 Kelvin, about minus 269 degrees Celsius. Just a few degrees above absolute zero, and its liquefaction required both technical ingenuity and an almost obsessive patience. On's achievement earned him the 1913 Nobel Prize in Physics, but its true significance would only become clear over time. By making helium liquid, he had created a tool that could probe the behavior of matter in regimes where thermal motion, the random jostling of atoms that dominates ordinary physics, virtually ceases, allowing quantum effects to emerge in their purest form. Only 3 years later, in 1911, Ons made a discovery that would transform both science and technology. While measuring the electrical resistance of mercury at increasingly low temperatures, he noticed something extraordinary. At about 4.2 K, the resistance suddenly dropped to zero, not gradually, but abruptly, as if a switch had been thrown. The mercury became a perfect conductor, capable of carrying electric current indefinitely, without any energy loss. Ons had discovered superconductivity, a phenomenon that classical physics could not explain. For decades, scientists could only describe what they saw without understanding why it happened. But they suspected that quantum mechanics, which was still in its infancy, held the key. The next great surprise came in 1937, when Soviet physicists Pyotr Kapitsa and John F. Allen, working independently in Cambridge, discovered that liquid helium itself underwent a strange transformation at 2.17 K. Below this temperature, the so-called lambda point helium-4 became a superfluid, a quantum liquid with zero viscosity. It could flow through the tiniest cracks, climb the walls of its container, and remain in motion without any apparent friction. If superconductivity was electricity's quantum trick, then superfluidity was nature's fluid counterpart, a state where the usual rules of resistance and dissipation no longer applied. The behavior of these quantum systems was so alien to intuition that even the most experienced physicists struggled to grasp it. In superconductors, electrons, normally repelled by their like charges, somehow formed bound pairs, known as Cooper pairs, which moved through the atomic lattice without scattering, thus eliminating resistance entirely. This pairing mechanism, first explained by John Bardeen, Leon Cooper, and Robert Schrieffer in 1957 in what became known as the BCS theory, is one of the triumphs of post-war physics. It showed that the electrons were not acting independently, but were linked through subtle vibrations in the crystal lattice, a collective quantum dance that allowed them to slip through obstacles that would stop them individually. The laboratory conditions required to study these effects were themselves a kind of technological poetry. Cryostats, insulated chambers filled with liquid helium, became standard tools in physics labs. Their polished steel walls hiding delicate glass apparatuses and sensors, capable of detecting minute changes in temperature and magnetic fields. The faint hiss of evaporating helium was a constant companion, and researchers spoke of the whisper of the quantum world becoming audible in those extreme conditions. Every experiment was a careful ritual, cooling the sample, monitoring the transition, recording the sudden, almost magical disappearance of resistance or viscosity. These discoveries were not just scientific curiosities. They had profound implications for technology and for our understanding of the universe. Superconducting magnets became essential for particle accelerators, enabling the enormous magnetic fields required to steer and focus high-energy beams. They also became the backbone of magnetic resonance, imaging MRI, transforming medical diagnostics. Superfluid helium found use in ultrasensitive gyroscopes and low-temperature detectors. While the principles uncovered in these experiments inspired new fields such as quantum computing, where the manipulation of quantum states relies on controlling matter at similar extremes, yet perhaps the most profound legacy of this cold revolution was philosophical. It forced physicists to confront the fact that quantum mechanics was not confined to the microscopic world of electrons and photons, but could manifest itself on a macroscopic scale, producing phenomena visible to the naked eye. A wire carrying a current forever without a power source, a liquid climbing walls as if defying gravity. These were not metaphors or mathematical abstractions, but real, tangible evidence that the universe, even at its largest scales, was shaped by the same strange principles that governed the behavior of atoms. By the middle of the 20th century, these low-temperature experiments had transformed our understanding of matter's fundamental nature. They revealed that resistance, friction, and dissipation, the forces we take for granted as inevitable, are not immutable laws, but emergent properties that can vanish under the right conditions. They showed that particles, when cooled into quiet cooperation, could achieve feats that no single particle could manage alone. And they reminded scientists that the universe often reveals its deepest truths, not in the heat of explosions or the glare of high-energy collisions, but in the silence of a lab where helium drips gently across the floor and where, in the coldest places imaginable, nature whispers its most beautiful secrets. By the mid-20th century, quantum mechanics had grown from a strange and controversial theory into a remarkably successful framework for describing the physical world. It could predict the behavior of atoms and molecules, explain the structure of stars, and account for the properties of materials that powered the modern age. And yet, beneath all that success lay a nagging unease, a suspicion that the theory, for all its predictive power, left something crucial unexplained. This unease had been there from the beginning. It was present in Albert Einstein's debates with Niels Bohr at the Solvay Conference of 1927, and it crystallized most famously in 1935, when Einstein, together with Boris Podolsky and Nathan Rosen, published a paper describing a thought experiment that would come to be known as the EPR paradox. The paradox was meant to expose what they believed was an incompleteness. In quantum mechanics, a place where the theory's mathematical description clashed with any reasonable notion of physical reality. The scenario they described was simple, yet deeply unsettling. Imagine two particles created together in such a way that their properties, for example, their spin, are perfectly correlated. If one particle is measured and found to have upspin, the other must instantly have downspin, no matter how far apart they are. According to quantum mechanics, until a measurement is made, neither particle has a definite spin. Instead, they exist in a superposition of possible states. But the moment one is measured, the other seems to know instantly what value it must take. Einstein called this spooky action at a distance, a phrase that revealed just how troubling he found the idea. It seemed to suggest that quantum mechanics allowed instantaneous influences to travel across space, something that appeared to violate the very spirit of special relativity, which limited the speed of any influence to the speed of light. For decades, the EPR paradox remained more philosophical than experimental. Physicists could calculate the predictions of quantum theory and verify them with extraordinary precision. But they could not directly test whether nature really behaved in such a non-local, interconnected way. It was not until the 1960s that a solution began to emerge. Thanks to the work of a soft-spoken Irish physicist named John Bell, born in 1928 in Belfast, Bell approached the problem from a different angle. Rather than arguing about what quantum mechanics might mean, he asked a more concrete question. Could any hidden variable theory a theory in which particles had definite properties before measurement, but those properties were simply unknown, reproduce all the predictions of quantum mechanics? And if not, could an experiment be designed to tell the difference? The result, published in 1964 as on the Einstein-Podolsky paradox, was one of the most profound contributions to modern physics. Bell derived a mathematical inequality, now known as Bell's inequality, that any local hidden variable theory must obey. If experiments showed that nature violated this inequality, it would mean that no such theory could explain quantum correlations. The implication was staggering. The universe would have to be non-local in some sense, with entangled particles sharing connections that defied classical intuitions. About space and separation, it took another decade before technology caught up to Bell's insight. But when it did, the results were unmistakable. In 1972, American physicists Stuart Friedman and John Clauser performed the first experimental test of Bell's inequality using entangled photons, and the results agreed with quantum mechanics, showing a clear violation of the inequality. Over the next decade, increasingly sophisticated experiments by Alain Aspect and his team at the Institut d'Optique in France, culminating in a landmark series of tests between 1981 and 1982, closed many of the loopholes and confirmed that entanglement was real, not a quirk of equations or a philosophical puzzle, but a physical feature of the universe itself. The implications of these results were profound and unsettling in equal measure. Entangled particles, once linked, behaved as if they were part of a single system, no matter how far apart they were separated. Measure one, and the other responded instantly, not because a signal traveled between them in the conventional sense, but because the concept of separate no longer seemed to apply. Space, which classical physics had treated as an arena where independent events unfolded in isolation, appeared to be stitched together by threads of correlation that ignored distance. The universe, Bell's work suggested, was not a collection of independent parts, but a deeply connected whole. This realization sent a quiet shiver through physics, one that has never fully faded. It forced scientists and philosophers to rethink ideas about reality, causality, and even the nature of information. It also laid the groundwork for new technologies: quantum cryptography, quantum teleportation, and the emerging field of quantum computing all rely on entanglement as a resource, using its strange correlations to achieve feats that classical systems cannot match. What began as a theoretical curiosity, a spooky prediction Einstein hoped would reveal a flaw in quantum mechanics has become a cornerstone of 21st century science and technology. Today, when physicists speak of Bell's theorem, they do so with a kind of reverence. It is more than a mathematical result. It is a bridge between the abstract world of quantum theory and the physical reality we inhabit. It shows that the universe is not a set of isolated points, but a web of relationships, where what happens in one place can be inseparable from what happens in another, even across vast distances. It suggests that the separations we see between particles, between objects, even perhaps between ourselves and the cosmos, may be illusions born of perspective. Beneath the surface, the world is woven together by connections that cannot be silenced. No matter how far apart their voices seem to be in the summer of 1997. In a quiet Austrian city surrounded by jagged mountain ridges and cool alpine air, a small group of physicists carried out an experiment that, for much of human history, would have belonged firmly to the realm of fantasy. They were based at the University of Innsbruck, a centuries-old institution nestled among narrow medieval streets and high snow-dusted peaks. And their work was not taking place in a sprawling high-tech laboratory or a sprawling particle accelerator, but in a modest series of rooms, linked by carefully aligned optics benches, precision lasers, and detectors sensitive enough to capture the faintest flicker of light. What they achieved there would make headlines around the world and mark a turning point in the story of quantum physics. For the first time, they successfully teleported the state of a particle from one place to another without physically moving the particle itself. To understand why this was such a remarkable moment, it helps to remember that for decades physicists had dreamed about the possibility of transmitting information instantaneously across space. Not in the science fiction sense of beaming up people or objects as in a television show, but in the subtler and more profound quantum sense, transferring the very state of a system, the invisible pattern that defines it without sending the system itself. The key to this dream lay in entanglement, the same phenomenon that John Bell had explored theoretically in the 1960s, and that experiments by Elling Aspect in the early 1980s had confirmed as a real feature of the universe. When two particles become entangled, their properties become so deeply linked that measuring one instantly affects the state of the other, no matter how far apart they are. This strange, non-local connection seemed to offer a tantalizing possibility, if one could manipulate entangled particles cleverly enough. Perhaps it would be possible to transfer the state of a particle from one location to another, destroying it in the original and recreating it perfectly at the destination. The team in Innsbruck, led by Anton Zeilinger, approached this challenge with both patience and ingenuity. They did not attempt to teleport physical objects, of course, no atoms or molecules, much less people, but rather the quantum state of a single photon, a particle of light. The setup was elegant but delicate. First, they created a pair of entangled photons using a nonlinear crystal and a precisely tuned laser beam. One photon from the pair was kept in the sending station, while the other was sent along a carefully aligned optical path to a receiving station, located several meters away in another part of the laboratory. Then, a third photon, the one whose state they wished to teleport, was introduced. By performing a joint measurement on this photon and the first of the entangled pair, they effectively erased the original state, but, thanks to the strange logic of quantum mechanics, simultaneously transferred that state onto the distant partner photon. The result, when confirmed, was astonishing. The receiving photon, which had never interacted directly with the original, now possessed its exact quantum state. Information had been transmitted not through a classical signal or a physical particle, moving across space, but through the deep, invisible correlations of entanglement. It was a feat that would have seemed impossible even to many of the pioneers of quantum theory. Albert Einstein, who derided entanglement as spooky action at a distance, had died decades earlier believing that such a phenomenon could never be real. Yet here it was, not as speculation or metaphor, but as a repeatable laboratory result, one that could be measured, verified, and published. The achievement in Innsbruck was not just a clever trick. It was a demonstration that the rules of quantum mechanics could be harnessed in ways no one had seriously imagined when they were first formulated. The implications were vast. Quantum teleportation, while incapable of moving matter instantaneously, offered a way to transmit information securely and with perfect fidelity, a concept that would become the cornerstone of quantum communication networks and quantum computing in the decades that followed. It also hinted at the possibility of a future quantum internet, where entangled particles distributed across vast distances could synchronize devices, encrypt data, and even link quantum processors separated by continents. The Innsbruck experiment also forced physicists to confront once again the philosophical strangeness of the quantum world. In classical physics, information is tied to matter. To move one, you must move the other. But in the quantum realm, the distinction is less clear. A particle state, its defining information, is not a physical substance that travels like a parcel in the mail. Instead, it is a pattern woven into the fabric of reality itself. An entanglement allows that pattern to be reconstructed elsewhere without ever crossing the space in between. It is as if nature, at its deepest level, cares less about the path information takes than about the relationships that link one part of the universe to another. Since 1997, experiments have pushed the boundaries of quantum teleportation far beyond the walls of Zillinger's laboratory. Teleportation has been demonstrated across 16 kilometers of free space in China, over 143 kilometers between islands in the Canary Archipelago, and even between satellites and ground stations orbiting hundreds of kilometers above the Earth. Each new milestone brings the dream of global quantum communication closer to reality. Yet for all its futuristic promise, the essence of what happened in Innsbruck remains profoundly simple. Two particles, entangled in a way that Einstein once dismissed as impossible, allowed information to leap without crossing, proving that the universe is woven together in ways that still defy our deepest intuitions. On that quiet night in 1997, as lasers cut through the faint alpine mist and detectors clicked softly in the darkness, science fiction took a small but decisive step toward fact. The experiment did not transport ships or people, but it showed that information, the most precious substance in a quantum universe, could flow in ways that ignore the usual boundaries of space. It was a whisper from the future, carried not by radio waves or fiber optics, but by photons entangled across space. A glimpse of a world where distance is no longer a barrier, and where the very fabric of reality itself can be rewritten with light. In the early decades of the 21st century, long after the first computers had shrunk from room-sized machines full of worry gears and vacuum tubes into devices that fit in the palm of a hand, a new kind of computation began to emerge, one that did not rely on the predictable switching of silicon transistors, but on the fragile, almost ghost-like behavior of quantum particles themselves. It was not born in garages or hobbyist workshops the way the personal computer revolution had. It's begun in the 1970s, but in sealed laboratories kept colder than any place on Earth, where vacuum chambers gleamed under soft blue light and tall, cylindrical fridge towers descended like mechanical stalactites from the ceiling. Inside these strange new machines, atoms hovered in electromagnetic traps. Superconducting loops pulsed with microwave fields, and particles too small to see shimmered in states that were neither 0 nor 1. But something far more mysterious in between. The idea of a quantum computer traces its origins back to the early 1980s, when physicists like Richard Feynman and Yuri Manin pointed out that classical computers, no matter how powerful, were inherently ill-suited to simulating quantum systems. A machine that processed information in bits, binary units that could be either 0 or 1, would always struggle to model a universe that at its most fundamental level existed in superpositions of states. But if a computer could itself operate using quantum principles, it might be able to solve certain classes of problems exponentially faster than any classical machine ever could. This was the bold vision that began to take shape in the following decades, and by the turn of the millennium, research groups from IBM, MIT, Oxford, and other institutions were building the first prototypes of what would one day be called quantum processors. At the heart of these machines are qubits, the quantum counterpart to the classical bit. A bit is simple and rigid. It is either 0 or 1, on or off, but a qubit. Because it obeys the rules of superposition, can exist in a combination of both states at once. Even more intriguingly, multiple qubits can become entangled, meaning their states are linked in ways that defy classical logic, so that measuring one immediately affects the others, no matter how far apart they are. These two properties, superposition and entanglement, are what give quantum computers their astonishing potential. A register of just 50 qubits, for example, could in principle represent more possible states than there are atoms in the observable universe. And while not all those states are directly accessible, the parallelism they provide opens pathways to solving problems that would take classical supercomputers billions of years. Building a machine capable of harnessing these effects, however, is no simple feat. Qubits are extraordinarily delicate, prone to losing their quantum coherence at the slightest disturbance. The heat generated by the surrounding environment, stray electromagnetic fields, or even a passing cosmic ray can collapse their superpositions and destroy the entanglement that makes them useful. To prevent this, quantum computers are typically operated at temperatures close to absolute zero, often around 10 millikelvin, colder than the depths of interstellar space. This is why quantum labs are filled with massive cryogenic refrigerators, towering devices that cool their contents in carefully stepped stages and shield them from noise and vibration. Inside, qubits take many forms: ions held in electromagnetic traps and manipulated with laser pulses, superconducting circuits that carry currents without resistance, and even tiny diamond defects that behave like artificial atoms. From the outside, these machines look nothing like the beige boxes that sit under office desks. They resemble futuristic sculptures, gleaming gold cylinders suspended from steel frames, draped with bundles of cables that transmit microwave signals and control pulses. The air hums with the sound of vacuum pumps and cooling systems, and the workspaces around them are lit by the glow of monitors streaming data from experiments that last hours or days. Physicists, engineers, and mathematicians huddle together in these rooms, tuning parameters, refining error correction codes, and coaxing fragile qubits into longer-lived states. Each successful measurement is a small triumph, a step toward a future where quantum computers can outperform even the fastest classical machines in specific, crucial tasks. That promise is immense. Quantum computers could revolutionize fields as diverse as cryptography, materials, science, and artificial intelligence. Algorithms such as Shor's algorithm, developed in 1994, show that a sufficiently powerful quantum computer could break widely used encryption systems by factoring large numbers, exponentially faster than classical computers can. Others, like Grover's algorithm, could accelerate database searches or optimize complex systems with unprecedented efficiency. Quantum simulation could allow scientists to model the behavior of molecules and chemical reactions in exquisite detail, paving the way for new drugs, catalysts, and materials that are currently beyond reach. The ability to solve optimization problems from logistics and finance to climate modeling could transform industries and reshape global economies. Yet, alongside that promise lies a deep undercurrent of peril and uncertainty. The same computational power that could unlock cures and materials could also render today's encryption obsolete, exposing financial systems and state secrets alike. The very fact that quantum computing challenges the foundations of classical information theory raises profound questions about privacy, security, and control. Governments are investing heavily in quantum research not only for the technological advantages it might offer, but also out of fear that adversaries might get there first. In this sense, the race to build a large-scale, fault-tolerant quantum computer echoes the nuclear race of the 1940s, albeit with equations and cryostats replacing reactors and bombs. For now, fully functional quantum computers remain more promise than reality. The largest prototypes, built by companies like Google, IBM, and INQ, operate with only a few hundred qubits, many of which are consumed by error correction. But progress is steady, and each year brings improvements in coherence times, gate fidelity, and scalability. What was once a theoretical concept has become a tangible, if still fragile, technology. And the shimmering qubits inside those frigid machines are already solving small problems that classical computers cannot. The age of quantum computing will not arrive all at once, but creep into our world gradually, just as the first electronic computers did in the mid-20th century. It will begin with specialized tasks, simulating molecules, optimizing networks, verifying complex proofs, and then expand outward, transforming industries and reshaping how humanity processes information. And when it does, we will look back at these early laboratories at the golden fridge towers, the whispering vacuum chambers, the qubits suspended on the knife edge of existence, and see in them the first glimmers of a new era, a time when computation ceased to be a mechanical process of switching bits and became something subtler and stranger, the orchestration of quantum states themselves. In the spring of 1957, a young American physicist named Hugh Everett III walked the halls of Princeton University carrying a dissertation that he believed could change the way humanity understood reality itself. He was only 26 years old. A recent graduate student under the guidance of John Archibald Wheeler, one of the most influential theoretical physicists of the era, and yet his ideas reached far beyond the usual ambitions of an academic thesis. They did not propose a new equation or offer a technical refinement of quantum theory. Instead, they attempted to answer a question that had haunted physics for decades, a question born in the smoky debates of Copenhagen between Niels Bohr and Albert Einstein. What actually happens when a quantum system is observed? Does the wave function, the mathematical description of all possible outcomes, truly collapse into a single reality when measured? Or is something deeper and stranger taking place behind the scenes? Everett's answer was as audacious as it was unsettling. He proposed that the wave function never collapses at all. Instead, every possible outcome of a quantum event actually occurs, not in the same universe, but in branching, parallel universes that split off from one another each time a measurement is made. In one branch, a particle might be measured as spinning up, while in another, it spins down. In one world, a cat in Schrödinger's box lives. In another, it dies. Reality, according to Everett, is not a single thread winding its way through time, but an endlessly branching tree of possibilities, with new universes sprouting continuously from every quantum decision. This vision, which would later come to be known as the many worlds interpretation, redefined the problem of quantum measurement. There was no mysterious collapse, no special role for observers. The mathematics of quantum mechanics describe the entire multiverse, and what we perceive as randomness was merely the experience of following one branch among countless others. But revolutionary ideas are not always welcomed. Everett's was met with skepticism, even hostility, from many of the most respected physicists of the time. Bohr himself dismissed it as metaphysical speculation, while others, including Wolfgang Pauli and Leon Rosenfeld, considered it unnecessary or even absurd. The Copenhagen interpretation, with all its philosophical difficulties, was deeply entrenched, and few were willing to accept a picture of reality that multiplied worlds by the trillions, just to preserve the linearity of the Schrödinger equation. Even Wheeler, Everett's advisor, admired his student's intellect but urged him to soften his claims, suggesting that perhaps the idea should be presented as a mathematical curiosity rather than a literal description of nature. Everett's defense of his theory was earnest but often lonely. He presented his ideas in seminars and private conversations, only to be met with polite silence or puzzled objections. In Copenhagen, he met Bohr personally to discuss his interpretation, but the meeting ended without resolution, leaving Everett frustrated and disheartened. He returned to the United States convinced that his work would never be taken seriously. Within a year of completing his dissertation, he left academic physics entirely, taking a position with the Pentagon's Weapons Systems Evaluation Group, where he spent the rest of his career working on nuclear strategy and systems analysis, a stark contrast to the cosmic grandeur of the ideas he'd once championed. Yet the many worlds idea did not die. It lingered in the margins of physics for decades, kept alive by a small number of thinkers who saw its strange elegance. In the 1970s, Physicists like Bryce DeWitt revived and expanded upon Everett's work, giving it a name and placing it at the center of a growing conversation about the nature of quantum reality. Gradually, what had once been dismissed as speculation began to be seen as a serious, controversial alternative to the Copenhagen view. Experiments continued to confirm the linearity and completeness of quantum mechanics, lending indirect support to Everett's contention that there was no fundamental reason for wave function collapse. And as the field of quantum cosmology developed, dealing with the universe as a whole rather than isolated particles, the idea of a universal wave function branching into many worlds began to seem not just plausible, but almost inevitable. The philosophical implications of Everett's proposal are difficult to overstate. If he was correct, then every quantum event, every radioactive decay, every photon passing through a slit, every neuron firing in a human brain spawns a multitude of parallel universes, each as real as the one we inhabit. There is a version of you reading these words and a version that never encountered them. A version of Earth where history unfolded exactly as it did, and another where it diverged centuries ago. The universe, once thought to be a singular and unique entity, becomes a vast, branching multiverse, infinite in its variations and eternally expanding with every moment of time. This picture is both wondrous and deeply unsettling. It suggests that reality is far larger and stranger than we can ever perceive, that the choices we make do not eliminate possibilities but merely select the path we happen to experience. Also raises profound questions about identity, causality, and even free will. If every decision spawns a universe, are we truly choosing, or merely following one thread among an infinite number? And if all outcomes occur, what does it mean to speak of probability at all? Today, Everett's ideas are taken far more seriously than they were during his lifetime. They underpin certain approaches to quantum computation, influence interpretations of cosmology, and inspire both philosophical debates and works of fiction. Yet they remain controversial, precisely because they challenge our most basic intuitions about reality. Everett himself did not live to see the rise of his theory. He died in 1982 at just 51 years old, never fully aware of how profoundly his once dismissed idea would shape the future of physics. And yet, in a sense, his vision was always larger than one life. In some universe, perhaps, his work was embraced immediately, and he continued his research. In another, it was forgotten entirely. If many worlds is true, then all of these stories exist, side by side, unfolding endlessly across the vast, invisible. The landscape of possibility, a gentle but disquieting reminder that the universe may be far bigger and far stranger than anything we can imagine. For centuries, the concept of a vacuum was understood as the simplest thing imaginable, an empty void, space completely devoid of matter, energy, and activity. Philosophers like Aristotle denied that such a thing could even exist, while later scientists like Evangelista Torricelli and Otto von Guericke in the 17th century demonstrated that a vacuum could indeed be created by removing air from a chamber, leaving behind what they believed was a perfect nothingness. Even Isaac Newton, who revolutionized physics with his laws of motion and gravity, thought of space as an inert backdrop, a vast and silent stage, upon which the drama of the universe unfolded. Yet the rise of quantum theory in the 20th century would overturn that ancient intuition, revealing that the vacuum was not silent at all. Beneath the apparent emptiness of space lay a restless, seething reality, a universe alive with fluctuations, energy, and invisible fields that refused to stay still even when stripped of everything else. The first hints of this deeper structure came with the development of quantum field theory in the early decades of the 20th century. As physicists like Paul Dirac, Wolfgang Pauli, and Werner Heisenberg worked to reconcile quantum mechanics with special relativity, they found that particles could no longer be treated as tiny, isolated points moving through empty space. Instead, they were excitations of underlying fields that filled all of space, vibrating and fluctuating even when no particles were present. According to this new framework, the vacuum was not the absence of everything, but the lowest possible energy state of these fields. And even this ground state was not truly zero. It contained what came to be known as zero-point energy, a residual energy that could never be removed because of the Heisenberg uncertainty principle, which states that one cannot simultaneously know a particle's position and momentum with perfect precision. Even in their lowest state, quantum fields had to jitter, their fluctuations producing a background hum that pervaded all of space. This concept was profoundly counterintuitive. How could empty space, stripped of matter and radiation, still contain energy? The answer lay in the nature of quantum reality itself. Particles and fields were not static objects, but dynamic phenomena, constantly flickering in and out of existence. Virtual particles, pairs of particles, and antiparticles spontaneously appeared and annihilated each other in unimaginably brief intervals. Their effects measurable, even if the particles themselves could never be directly observed. What had once seemed like a void was now understood as a kind of cosmic foam, alive with fleeting events that hinted at the deep, underlying structure of the universe. The reality of this hidden energy was made strikingly clear by an experiment proposed by the Dutch physicist Hendrik Casimir in 1948. Casimir predicted that if two uncharged, parallel metal plates were placed very close together, separated by only a few micrometers, they would experience a tiny but measurable force pushing them together. Even in a perfect vacuum, this force, now known as the Casimir effect, rises because the quantum fluctuations of the electromagnetic field are slightly different between the plates than outside them. In the narrow gap, only certain wavelengths of virtual photons can exist, while outside, a broader range is allowed. The imbalance in pressure effectively pushes the plates together, as if the vacuum itself were exerting a force. When the effect was first measured experimentally in the 1950s, and more precisely in the 1990s, the results confirmed Casimir's prediction with remarkable accuracy. Empty space, it seemed, was not empty at all. It was a dynamic medium capable of producing real, measurable forces. This discovery had profound implications not only for fundamental physics, but also for emerging technologies. Engineers designing microelectrometallic systems, MEMS for example, must account for Casimir forces, which can cause tiny components to stick together unexpectedly. On a more speculative level, the vast reservoir of zero-point energy has even inspired proposals for futuristic propulsion systems and energy extraction. Though such ideas remain far beyond our current capabilities, the notion that the vacuum is alive with energy also plays a crucial role in cosmology. The cosmological constant, introduced by Albert Einstein in 1917 and later reinterpreted as a manifestation of vacuum energy, is believed to drive the accelerated expansion of the universe. In modern terms, this mysterious repulsive force is associated with dark energy, which makes up roughly 68% of the total energy content of the cosmos. Although its precise nature remains one of the deepest mysteries in science, many physicists believe that it is intimately connected to the zero-point fluctuations that pervade space. What makes these ideas so extraordinary is how they challenge our most basic intuitions about reality. The vacuum, once thought of as a passive nothingness, is now seen as an active participant in the workings of the universe. Its fluctuations influence the behavior of particles, its energy shapes the expansion of the cosmos, and its subtle forces can be measured in the laboratory. Even the light that travels across billions of light years, carrying the history of galaxies and stars, does so through a medium that is anything but empty. The vacuum hums, vibrates, and whispers beneath the fabric of existence. A reminder that stillness is an illusion, and that motion and energy are woven into the very nature of reality. In the end, listening to empty space is not about hearing a literal sound, but about recognizing the subtle background against which all things unfold. It is the quiet murmur of virtual particles blinking into and out of existence, the pressure that nudges metal plates together in a laboratory. It's the force that stretches the fabric of the cosmos itself. It is the universe telling us, in the softest possible voice, that nothingness is not nothing, that even in the absence of matter, the stage on which reality plays out is alive, dynamic, and endlessly creative. And in that realization lies one of the most profound truths of modern physics. that the vacuum is not a void to be ignored, but a fundamental feature of existence, the hum, beneath everything that is. By the time the 20th century drew to a close, quantum mechanics and its towering companion, the Standard Model of particle physics, had proven themselves to be among the most successful scientific theories ever constructed. They explained with astonishing precision how fundamental particles behaved and interacted, from the electrons in atoms to the quarks inside protons and neutrons. They predicted the existence of particles like the W and Z bosons, discovered at CERN in 1983, and the Higgs boson, confirmed at the Large Hadron Collider LHC in 2012, decades after theorists first proposed it. And yet, for all their success, these theories left too many questions unanswered. They did not explain why the universe contains far more matter than antimatter, nor did they account for the mysterious dark matter that outweighs ordinary matter by a factor of 5. They said nothing about dark energy, which seems to drive the accelerating expansion of the cosmos. And they could not reconcile quantum physics with general relativity, the theory that describes gravity and the structure of space-time itself. It was clear that something deeper must lie beyond the Standard Model, a hidden layer of rules that remained just out of reach. The search for that deeper layer has taken physicists into some of the most extreme environments on Earth, and has driven them to build machines and experiments of staggering size and sensitivity. Deep beneath the mountains of Italy, inside the Gran Sasso National Laboratory, detectors the size of buildings sit shielded from cosmic rays by more than a kilometer of rock, waiting for the faintest signals from particles that rarely interact with anything at all. At the Sudbury Neutrino Observatory in Canada, physicists filled a 12-meter-wide acrylic sphere with 1,000 tons of heavy water and surrounded it with nearly 10,000 photomultiplier tubes to detect the ghostly passage of neutrinos, nearly massless particles that stream through the Earth by the trillions every second, yet almost never collide with anything. In Antarctica, the Askew Neutrino Observatory has transformed a cubic kilometer of ice beneath the South Pole into a vast cosmic detector, using strings of sensors buried deep below the surface to capture the faint flashes of light produced when a high-energy neutrino interacts with the ice. These extraordinary experiments are motivated by a profound puzzle: the realization that the matter we can see, stars, planets, gas clouds, galaxies, makes up less than 5% of the total content of the universe. The rest is invisible, detectable only through its gravitational effects. Dark matter, first inferred by astronomers like Fritz Zwicky in the 1930s and later confirmed through the rotation curves of galaxies, measured by Vera Rubin in the 1970s, exerts a powerful gravitational pull, yet neither emits nor absorbs light. Countless attempts to detect it directly have so far failed. Experiments like Lux Zeppelin in South Dakota and Xenon in Italy use massive tanks of liquid, xenon cooled to cryogenic temperatures, searching for the tiny flashes of light that might be produced if a dark matter particle collides with an atomic nucleus. Years of data taking have produced tantalizing hints but no definitive detection. Yet the search continues with relentless determination. Another frontier lies in the hunt for supersymmetry, a bold theoretical framework proposed in the 1970s that extends the Standard Model by pairing every known particle with a heavier, unseen superpartner. Supersymmetry could explain why fundamental particles have the masses they do, solve deep mathematical inconsistencies, and even provide a candidate for dark matter. But despite decades of searching, including high-energy collisions at the LHC, reaching energies of 13 teraelectron volts, the superpartners have yet appeared. Their absence has forced physicists to question whether supersymmetry exists at all, or whether nature's deeper rules lie along a different path. The search also extends into the realm of neutrinos, those elusive ghost particles that are so abundant yet so difficult to study. Once thought to be massless, they were shown in 1998 by the Super Kamiokande experiment in Japan to oscillate between different types, a discovery that implied they must have mass, however small. This revelation opened new questions about their role in the evolution of the universe and their possible connection to the matter-antimatter imbalance. Future experiments, such as Dune Deep Underground Neutrino Experiment in the United States, aim to explore these mysteries by firing powerful neutrino beams over thousands of kilometers and observing how they change as they travel, what unites all. These efforts, from the detectors buried under mountains to the sensors frozen deep in Antarctic ice, is a shared quality of human stubbornness, a refusal to accept that our current picture of the universe is complete. Physicists spend decades designing instruments sensitive enough to detect a single particle interaction amid trillions of false signals. They sift through mountains of data, chasing faint statistical anomalies that might point to new physics. They question their assumptions, refine their models, and build ever more ambitious experiments, all in pursuit of answers that might forever elude them. And yet, even without definitive results, the journey itself has deepened our understanding of nature. The absence of supersymmetric particles at the LHC, for example, has narrowed the range of possible theories and forced physicists to consider alternatives such as extra dimensions, composite particles, or entirely new forces. The study of neutrinos has revealed that they play a far more complex role in the cosmos than anyone suspected. And every new constraint on dark matter, every experiment that does not find it, brings us closer to understanding what it might be. The quest beyond the standard model is not about immediate triumph, but about patience and persistence, about listening for whispers in the noise of the universe and refusing to stop even when the silence stretches on for decades. It is a testament to the human desire to know, to look into the darkness and believe that something is there waiting to be found. And though the answers remain hidden, the pursuit itself has already transformed physics, showing us that the universe is not a finished story but a vast, unfinished manuscript, with entire chapters still unwritten and waiting to be discovered for most of the 20th century. Quantum mechanics was treated as something that belonged almost exclusively to the domain of physicists and their elaborate machines, a set of rules that govern the subatomic world of electrons, photons, and nuclei, relevant only in the cold, controlled confines of laboratories or in the unimaginable violence of stars. It was a science of precision instruments and chalkboard equations, not of forests or fields, not of birds wheeling through the sky or flowers reaching toward the sun. Yet as the century drew to a close and new experimental techniques allowed scientists to probe the inner workings of biological systems with unprecedented detail, a surprising truth began to emerge. Nature itself had been using quantum mechanics all along, quietly and efficiently, billions of years before humans ever gave it a name. Far from being a curiosity confined to particle accelerators and cryogenic chambers, quantum phenomena were woven into the fabric of life, guiding processes as fundamental as how plants capture sunlight and how birds find their way across continents. One of the most striking examples of this is photosynthesis, the process by which plants, algae, and certain bacteria convert sunlight into chemical energy. For decades, biologists understood the broad strokes of how this worked. Photons from sunlight strike pigment molecules in a structure called a light harvesting complex, exciting electrons and transferring energy to a reaction center where it is stored in chemical bonds. The process was known to be extraordinarily efficient. In some cases, more than 95% of the captured sunlight was converted into usable energy, but no one could explain why. According to classical physics, the energy from the absorbed photon should have hopped randomly from molecule to molecule, like a drunkard stumbling down a street, losing some of its vitality at each step. Yet somehow, the energy seemed to flow directly and almost flawlessly to its destination. The answer? Revealed by experiments in the 2000s using ultrafast laser spectroscopy, was that plants were exploiting a quantum effect known as coherence. Instead of moving randomly, the energy existed as a wave-like superposition, exploring multiple paths simultaneously and choosing the most efficient route to the reaction center. This quantum choreography happened on incredibly short timescales, femtoseconds, or quadrillionths of a second, and was so delicate that many physicists had assumed it would be impossible in the warm, noisy environment of a living cell. Yet evolution had found a way to make it work. stabilizing the process through molecular structures that protected coherence just long enough to give nature an extraordinary advantage. In effect, plants had mastered quantum optimization long before humans dreamed of building quantum computers, an equally astonishing example of quantum mechanics at work in the natural world can be found in the migratory behavior of birds. For centuries, scientists puzzled over how species like the European robin could navigate thousands of kilometers with such accuracy. Even on cloudy days when the sun and stars were hidden, magnetic compasses implanted in their beaks or magnetite crystals in their tissues were suggested as possible explanations. But none could fully account for the bird's sensitivity to the Earth's weak magnetic field. Then, in the 1970s and 1980s, researchers began to suspect that the answer might lie not in the bird's anatomy, but in their quantum biology. The leading theory today is known as the radical pair mechanism, and it suggests that birds use a quantum compass based on entangled electrons inside specialized proteins in the bird's retinas, proteins called cryptochromes. Photons of blue light trigger chemical reactions that create pairs of electrons whose spins are entangled, meaning their quantum states are linked even when separated. These spins are influenced by the Earth's magnetic field, subtly altering the outcome of the chemical reactions. The changes, scientists believe, create a visual pattern or sensation that allows the bird to see the magnetic field as a faint overlay on its surroundings, guiding its navigation with astonishing precision. The process occurs on timescales of microseconds and involves quantum coherence maintained under conditions room temperature, biological fluid, constant motion, that human engineers still struggle to replicate in the lab. These discoveries have profound implications not just for biology, but for our understanding of quantum mechanics itself. They show that nature, through the slow, blind trial and error of evolution, has found ways to use quantum effects under conditions that physicists long believed would destroy them. They suggest that quantum phenomena are not fragile oddities that vanish in the messy complexity of the real world, but fundamental tools that life has incorporated into its machinery. From the photosynthetic pigments of a forest canopy, capturing sunlight with quantum precision, to the starling flocks that trace invisible lines of magnetic force across the skies of Europe and Africa, nature is fluent in a language that humans are only beginning to learn. This realization is humbling. For decades, scientists assumed that quantum mechanics was too delicate for the chaotic, the thermal world of biology, that coherence and entanglement belong to the cold, controlled environments of superconducting circuits or the vacuum chambers of particle accelerators. But nature had been writing its own quantum code for billions of years, long before humans learned to read it. The forests and oceans have been running quantum computations every day. The cells of leaves in the retinas of birds, solving problems of energy and navigation with an elegance that no laboratory yet matches. And so, as we push forward into a future of quantum technologies, quantum computers, quantum sensors, quantum communication networks, we are, in a sense, catching up to what nature has already achieved. We are learning, slowly and imperfectly, to do in silicon and superconductors what evolution has been doing effortlessly in proteins and pigments. The lesson is both humbling and inspiring. The quantum world is not confined to the distant, the tiny, or the artificial. It is alive in the rustle of leaves as sunlight is captured and transformed, in the silent precision of a robin's journey across a continent, and in the countless invisible processes that make life possible. We are, it turns out, latecomers to a conversation that has been going on since the dawn of life, a conversation written in the language of probability, coherence and entanglement, whispered by nature long before we learned to listen. On a clear night far from the city, when the hum of traffic fades and the air grows thin and cold, the sky stretches outward like an ancient scroll written in a language older than life itself. To look up at it is to look into the past, not metaphorically, but literally, because every point of light that meets the eye is a messenger that has traveled through time. The faint glow of Proxima Centauri, our nearest stellar neighbor, left its surface more than 4 years ago. The soft light of the Andromeda galaxy, faint and ghostly on the edge of human vision, began its journey more than 2 million years before the first humans walked the Earth. Yet whether the source is near or unimaginably far, whether the light began its voyage from a newborn star or the cooling embers of a dying sun, all of it arrives here in the same way in quanta, discrete packets of energy, each one a tiny echo of the quantum universe that lies beneath everything. That simple fact, first glimpsed in 1905 when Albert Einstein described the photoelectric effect, still carries something quietly astonishing even now, more than a century later. Every photon that reaches our eyes on a starry night is a relic of the same laws that govern electrons in an atom or the behavior of particles in a laboratory accelerator. It is a reminder that the strange probabilistic world of quantum mechanics is not confined to the small or the artificial. It is woven into the cosmos itself, into the light that plants use to build sugars and that telescopes gather to map the structure of galaxies. Even the warmth we feel on our skin from the midday sun is a vast chorus of quanta, billions upon billions of photons streaming through space, each obeying the same simple but profound rules. And yet, for all the immensity of that universe and the relentless precision of its laws, there is something profoundly human about the act of observing it. Imagine a child standing beneath the same night sky, small fingers pointing upward toward a star whose light began its journey long before their grandparents were born. The universe may be vast beyond comprehension, but in that moment it becomes intimate, personal, almost playful. The photons that began their flight before the pyramids were built or before dinosaurs vanished now end their journey in the cells of a human retina, sparking impulses that race to the brain and become thought, memory, and wonder. That connection between something unimaginably old and something fleetingly young is one of the most beautiful consequences of the quantum world. It allows the universe to speak to us directly, not in words, but in light. When we study quantum mechanics in the classroom or in the lab, it is easy to lose sight of this poetry. We talk about wave functions and uncertainty principles, about superpositions and entanglement, and we forget that these abstractions are also the heartbeat of the cosmos. The stars do not twinkle because of human equations. They twinkle because of quantum processes unfolding in their cores, protons tunneling through barriers to fuse into helium, releasing photons that scatter and scatter again before finally escaping into the void. The cosmic microwave background radiation, that faint afterglow of the Big Bang still filling space after 13.8 billion years, is nothing less than a field of primordial photons, each one carrying the signature of a universe still in its infancy. Even the blackness between the stars is not empty but filled with virtual particles flickering into and out of existence, the vacuum's quiet whisper that underlies everything. It is humbling to realize that we exist for only a blink in this grand story. Human civilization, with all its achievements and anxieties, has lasted for the briefest fraction of cosmic time, a few thousand years of written history against billions of years of stellar evolution and planetary formation. The light that reaches us tonight will still be crossing space long after we are gone, long after our cities have crumbled and our languages have faded into silence. And yet, in that fleeting span, we have learned to read the universe's messages with remarkable clarity. We have built instruments that can detect the faintest photons from galaxies at the edge of the observable universe. We have measured the subtle polarization of light that reveals the structure of space-time itself. We have even begun to manipulate individual photons in laboratories, bending them to our will in experiments that test the very foundations of reality. But perhaps the most important lesson quantum physics has to offer is not about technology or control, but about perspective. It teaches us that the universe is both unimaginably vast and intimately connected, that the same principles governing the fusion of stars also guide the photosynthesis in a leaf or the firing of neurons in a brain. It reminds us that uncertainty and probability are not flaws in our understanding, but fundamental aspects of how reality itself unfolds. And it shows us that, for all our efforts to categorize and explain, there will always be something irreducible, something unknowable, at the heart of existence, standing beneath the night sky. It is easy to feel small, and in a way, we are. Yet there is a quiet dignity in that smallness. Because to be human is to be part of this vast story, to absorb starlight that began its journey before our species existed, to send our own signals out into the cosmos in search of answers, to teach small hands to point upward and wonder. The universe does not need us to notice it, and yet it is richer because we do. In the end, quantum physics is not just a theory about particles or probabilities. It is a language that connects us to everything, from the fire in the hearts of stars to the faintest flicker of light on a child's cheek. It is a reminder that even in the darkness, the universe is playful and alive, and that to wonder at it is to be fully human.